Starting from the energy balance equation, derive the equation to be solved to determine the adiabatic flame temperature. Now what I have written here is the energy balance equation that we've been using in class. And we can simplify this a little bit depending on our system. So if we start simplifying, we know that our flame is going to be a steady state system. So steady state system. And what that means is the rate of change of everything that we are putting into the system is zero. It's always going to be constantly the same thing. So if we take that into account, this entire left side of the equation becomes zero. Our delta Q, because we're in an adiabatic system as given in the adiabatic flame temperature definition, this also equals zero because in an adiabatic system, the heat change equals zero. Our small amount of work that we have, because we have no mixer in our system, this also equals zero. There's no work being done. And when we compare a flame, the changes in kinetic and potential energy, the potential energy doesn't change much because there isn't a big change in height. And the kinetic energy doesn't change much either. So we can say the kinetic and potential energies of all in and out equals zero. Just like that. And what we're left with is 0 equals H in dm in minus H out dm out. Written another way is H in dm in equals H out dm out. Or in English terms, total enthalpy in is going to equal the total enthalpy out. So total enthalpy in equals total enthalpy out. Just like this. Now, how would we go about calculating total enthalpy in and total enthalpy out? So if we use a little bit of intuition, we know that a total is a sum of all parts. And our parts in this equation being the different components that we have that we solved for in part 1 are methane, oxygen, carbon dioxide, water, and nitrogen. So if we want to find the total enthalpy of the entire everything we're putting in, we want to find the enthalpies of all the components that we're putting in. So we can say something like H in, our total enthalpy in, is going to equal a sum. Say I being all of our components, oxygen, nitrogen, carbon dioxide, methane, and water, the number of moles of each times the enthalpies of each, Hi, times the temperature, because we depend on temperature, and this temperature being temperature in, just like that. And we can do the same thing for the enthalpy out. So we can say H out is going to equal sum I, just like before, times Ni, the total number of moles going out, times the enthalpies of each, times the temperature out, just like that. And then that gives us another question. What is this enthalpy of each component? And we can actually solve for that because it depends on the temperature that we want. So we say, because it depends on temperature, I will call it Hi of T. And what we know when we're calculating this is the standard enthalpy of formation of an ideal gas. And what we're going to assume is this temperature that we are trying to find is going to be higher than that ideal gas temperature, which is 298.15. So this is going to equal the heat of formation, let me make this capital, Hf of each I And this, as I said, was the standard enthalpy of formation of an ideal gas. Standard enthalpy of formation of an ideal gas, Ig. And that's at 298.15 Kelvin. And what we're doing when we are making this equation or making this reaction happen, we are adding more enthalpy as we raise the temperature. So if we're adding more enthalpy, it's going to be a plus. But how much are we adding? We're adding the integral from the beginning ideal gas temperature, 298.15, to the final temperature that we're solving for, T, of Cp dt, just like that. And this equation here is what we are going to be using to find our final temperature. And we're going to do that within Python, encoding, and using some of the chemical engineering properties that we know to determine this final temperature. So we will do that in parts C and D.